All right, good afternoon, everyone. So I'm last but one. I'm very happy that a lot of you are sticking around for my talk. I was actually supposed to speak yesterday, but unfortunately I couldn't make it yesterday. I'd like to thank Steve Conway and Doug Code for inviting me to be here. This is my first presence at this HPC User Forum, and I've really enjoyed the talks. So I hope some of you will actually enjoy my talk. So I'm going to shift gears a little bit. This is completely different from what the previous speaker spoke about. This was supposed to be in the combustion session, so I apologize for this. But we are going to talk about how HPC can actually accelerate combustion engine design. So this is my outline. I'll talk a little bit about introduction. So I don't know how much you guys know about engines. So I'll talk about engines a little bit. I'll talk about the role of modeling and simulations in engines. I'll motivate why do we need exascale computing. This was actually a question that I had in my mind when I started my postdoc at Argonne, but now it's very clear to me that even an exascale is not enough for what we are trying to do. We'll talk a little bit about capacity computing and capability computing. I actually work a lot with the industry, and I know that industry is very interested in capacity computing. And we'll introduce this workflow manager called Swift that allows us to do high throughput capacity computing. Uncertainty quantification is typically not being used for engine simulations in general, so we have been pioneering the use of uncertainty quantification and machine learning tools for engine simulations. So we'll talk a little bit, give you one example of each. We work a lot with the industry. I don't have the time to give all the examples, but I'll give you one example just to give a flavor of how we work with the industry. Typically, when we work with the industry, one question that typically comes up, industry has clusters. They do not have supercomputer. So they typically ask us, when does it make sense to work on a supercomputer versus a cluster? So I have a couple of examples of when it makes sense to work on a cluster, whereas when it makes sense to go to a supercomputer. And then I'll introduce this Verify program at Argonne. This is really our forum to work with the industry. You can think of it as a consulting service for HPC. We'll talk a little bit, and I'll give you some take-home messages. So this is really the 21st century. Engines in the past have been designed like this, and car engines have been designed like this, actually. And they work well, surprisingly. But now we have supercomputers that are available. And supercomputers are really good for many things. They are good for multi-objective optimizations. They are good for uncertainty analysis, sensitivity analysis, etc. But really, to use simulations effectively, you need to ensure two things. The first thing is that your simulations are high fidelity across the design space that you're exploring. The second thing is the simulations need to have high throughput to explore the full design space. And this is often a concern when we speak to the industry, that high fidelity simulations are not fast enough, so the throughput is actually slow. So I have a video here that talks about what we are trying to simulate. So this is actually a video of an internal combustion engine. A car that you're driving has probably 4 or 6 cylinders. I'm just showing you one typical cylinder. You're looking at the cylinder head here. This is the piston bowl geometry. So the piston bowl geometry is coming up and down. You'll see these fuel spray parcels that are being injected. So this is really the gasoline fuel or the diesel fuel that's being injected into your car engine. And once they're injected it in a hot atmosphere. So they evaporate, they ignite, they combust. Once they combust, you actually get the heat release, and that's basically what drives your car. So I'll play this movie again. Let's see if it works. Yeah, so that's basically what's going on. But this is actually a very challenging problem. The movie looks cool, but to actually solve this is a very challenging problem. You need to resolve the flow inside the fuel injector, so that's a two-phase flow problem. It's very, very difficult to resolve the flow inside the injector. When you're driving your car, no two cycles of your car are actually the same. So there is a lot of cyclic variability from one cycle to another. That's very, very difficult to simulate. That involves getting the right turbulence model in there. Fuel chemistry is very challenging. It's actually large. Typically, simulations scale with cube of number of species that we have for fuel chemistry. And the fuel chemistry is actually different. If you go to your gas pump, you take octane rating of 97 versus 91 versus 95, the fuel chemistry is actually different. So how do we account for that? And then, of course, having correct emission models, doing the material issues correctly, doing the conjugate heat transfer, these are all very, very challenging problems. I often tell my postdocs that an engine is probably the most complicated HPC problem. I think many people in the room will disagree with me, but that's what I feel, because we have moving boundaries. We have Lagrangian parcels, adaptive meshing, very small time steps, very small length scales, and most importantly, we have densely embedded meshes. So it's a very, very complicated problem to actually scale. So the role of modeling and simulations for engines has typically been experimentally driven. So people spend a lot of effort in doing experiments, and they try to match their simulations, simplified simulations, to the experiments, and then they use those simulations to actually guide their design. So what we have been doing at Argonne is actually a transformational approach. So we are trying to implement higher fidelity combustion models, higher fidelity turbulence models, higher fidelity two-phase flow models, and then couple them together with the exascale architectures that are going to come online. And this hopefully will make us predictive. We are not there yet. We are really not doing predictive engine simulations yet, but that's sort of my job security for next 20 years. I hope we'll get there in 20 years. So the dream actually is to do a full engine simulation with fuel embedded in that, and to really do it in simulations by understanding all the uncertainties. It's very, very challenging, just because of what I said. The reality is that we are able to do some simplified engine simulations, and the uncertainties are poorly understood. So the transformation is really to develop this highly parallelized CFD code with fully integrated uncertainty quantification. And we are somewhere in the middle here, and we'll talk about some results as to how we are trying to do this transition. So this is a slide by my colleague, Dr. John Doerr. He's Director of Combustion Research at Cummins. We have had collaborations with him for the past 6 years. So the way he explains this is very interesting. So he says at Cummins, they do sector simulations. Instead of doing a full 360 simulation, they do a sector simulation. They use chemistry mechanisms which have about 50 species. They use RANS type of turbulence models. So if I were to ask him, what would it take him to get truly predictive? Of course, he has to do full 360. Of course, he has to have LES type of turbulence models. He has to resolve the flow inside the injector. He has to accurately model the spray physics. And 50 species to represent a complicated fuel is just not enough. You probably need 500 species. So if the turnaround time in the industry, typically at Cummins, is 24 hours. So they want to get their results in 24 hours. And typically when they do these sector calculations, they use 64 cores. Now all these are multiplicative, right? So if you want to do a truly predictive calculation, you actually need 500 times more cores. So our problem is actually an exascale problem. So we need 30 million cores to still get the turnaround time with these. And this doesn't even include uncertainty quantification. Uncertainty quantification is another layer over this, right? But what we have now is almost an exascale machine. So even if we had the whole machine, it wouldn't be enough to do this problem in a predictive manner, right? So that's why we resort to modeling. So we really classify our problems in two ways. One is capacity computing, one is capability computing. So on the left is capability computing. Here we do simulations using thousands of cores, and these simulations take a long time, often 2, 3, 4 weeks. And the data that we generate, we believe, is complementary to experiments, okay? And typically for industry, we do not do many of these. Industry likes capacity computing. That's what I'm showing here. Capacity computing is really having the ability to run thousands of cases very quickly. And even by doing capacity computing, we use thousands of processors, tens of thousands of processors. But typically, this is what is the preferred approach in the industry. So often engines are being designed by intuition of experimentalists, but typically if you rely on intuition, it doesn't work if you're trying to design a new combustion system. So what we have tried to do here at Argonne is we have imported this engine simulation code that's used in the industry quite often. It's called Converge. And we ported it to Mira. And in order to port it to Mira, it was really not designed for a supercomputer. So we did a lot of work. We did MPI-IO. We improved the load balancing schemes. We improved the interprocessor communication. And then the code was actually ready to run on the supercomputer. So once we were able to do that, we actually wanted to do a demonstration problem. Here we wanted to run about 10 to 12,000 simulations, each of these simulations running on 64 processors. So that way we would be using the whole of Mira. So the whole of Mira has about 768,000 processors. Okay? So why do we want to do this? It's basically to speed up, it's basically to get high throughput. Now, even if you have an army of postdocs, it's impossible to run 12,000 cases manually. So we integrated this workflow manager called Swift. It does a lot of these things in an automated fashion. I'm not going to go into the details into this, but this work was actually possible because of the core hours that we got through an ALCC program from ASCAR. And what did we learn from this? So we actually helped optimize a new combustion system. It's called gasoline compression ignition. And I'll come to this later in more detail. But typically, we demonstrated that we were running 2,000 simulations in 4 days, which typically in a cluster would probably take a couple of months. So really improving the throughput of our calculations. So I want to give maybe an Engines 101 lesson here. And there'll be a quiz after this. No, I'm kidding. But the 101 lesson here is that we at Argonne have been trying to design a gasoline compression ignition engine. Dr. Steve Ciatti has been leading this program for 7-8 years, and now Delphi is actually making a car out of this idea. So those of you who know engines, it sounds strange, right? Because diesel fuel is usually compression ignited, and gasoline fuel is actually spark ignited. So what we are talking about is compression igniting a gasoline fuel, okay? So that, in theory, shouldn't work, okay? But we have been able to make it work with the experimental work and also with simulations. So that's one of the examples that I'm going to give here. So a lot of the challenges of making it work were at idle conditions and low load conditions. And we were able to do a lot of calculations, a lot of simulations to actually guide the injection strategy, to guide the piston bowl design in order to do this. So I'm going to show you some examples, basically looking at these low load conditions and how we were able to achieve good combustion at these low load conditions. So we looked at different parameters that actually influence a combustion system. So a lot of these parameters are, for example, start of injection timing, the amount of fuel that's injected, the duration of injection of the fuel, the internal EGR, exhaust gas recirculation, how hot your piston bowl temperature should be, for example. So we looked at all these parameters and we assigned some uncertainties to it. Because we are doing it in a simulation, we also had models, right? So we also assigned some uncertainties to our model parameters. So these are really our boundary condition uncertainties, and these are our model parameter uncertainties. So we sort of couple them together, and we run thousands of calculations again, and we use this global sensitivity analysis tool that we have developed at Argonne. It's really a precursor to an uncertainty quantification tool. And we get really nice insights. For example, CA10 here is ignition delay. That's the amount of time it takes for the fuel to ignite once it's injected, okay? And we learned that pressure at intake valve closure is very, very important, and it actually guides the ignition delay. So we were able to provide a lot of insights like this to the combustion process that really helped our experimentalists design this engine. And here I'm showing you NOx, hydrocarbon emissions, carbon monoxide emissions, and we were able to demonstrate what input parameters, whether it's a model parameter or whether it's an experimental parameter, that was actually influencing the results. So if it's a model parameter, We understand what to do. If it's an experimental parameter, that's an input to the experimentalist, and they modify their design based on this. So this was a massive optimization problem then. Once we understood the uncertainties, the start of injection of the fuel was a big uncertainty, and we understood that if you inject the fuel too early, this is the same movie that I was showing earlier. It's just that, I don't know why it's not playing anymore. Yeah, this is the same movie I was showing earlier, but it's for different start of injection timings. SOI stands for start of injection. So if we inject too early, what we observe is that a lot of fuel actually goes into this thin squish region, and it doesn't burn properly. If we inject the fuel too late, I'm going to try and play it again. If we inject the fuel too late, we observe, so this is a late injection, we observe that the fuel doesn't have enough residence time to actually burn inside the combustion system. So what we learn is with CFD, high fidelity CFD, we were able to provide some guidance as to what should be the right injection timing. And then they went ahead and did the experiments and got a confirmation that indeed around 30 degree is a good timing. So this was a good success story for us. So I have a couple more examples. I talked about cyclic variability a little bit, saying that in an SI engine, no two cycles are same. So if you're driving your car, it's highly unlikely that two cycles of your car are the same. So in the engine community, there is a lot of interest in trying to understand the sources of cyclic variability. So for example, if you get a high cycle, your engine may knock. If your engine starts knocking many times, you can have a catastrophic failure of the engine. Many times if you have a low cycle, that means you have low pressures, your engine can actually misfire. And none of these are actually good for the engine. So experiments only provide some insights, but we are trying to use simulations and then to use some machine learning techniques to really understand what are the causes of these high cycles and low cycles. So we are using this random forest method. We understand that the standard regression techniques really do not work well when you have highly stochastic events. So we are trying to use random forest techniques to actually understand what are the sources of CCV. So here is another movie. This is work that we did with GM. Typically, what we try to do when we are trying to study CCV is we have to run many cycles, right? We have to run maybe 100 or 1,000 cycles because it's a very stochastic event. And running 100 or 1,000 cycles will take months to a year, depending on the computer access that you have. So what we have developed is a technique that allows us to perturb the initial conditions in a way that the statistics that we compute out of the CFD simulations are representative of running 1,000 cycles consecutively. Okay? So the GM guys actually ran 50 consecutive cycles that took them about 2.5 months. We actually ran 256 engine cycles in 10 days in Mira, so you can clearly see the change in, thank you. You can clearly see the high throughput that we are able to get by doing this. So typically our industry folks ask, when should we use a cluster? When should we use a supercomputer? What problems are good for a supercomputer? So we actually did this ROI analysis for them. So the goal here is lofty. We wanted to run 12,000 cases. Of course, we wanted to show that you want to run on a supercomputer. So we took a lofty goal of trying to run 12,000 cases. And we came up with scenarios. So if an engineer at GM, at best case, probably has access to 1,000 cores on a cluster, at worst case, he probably has access to 200 cores on a cluster. So if you want to run these 12,000 cases to really optimize a combustion system design, on Mira, you can get it done on 4 days, if David Martin is kind to us. But on a cluster, it may take 6 months. On a worst case scenario, it may take 3 years. Okay? So then if I try to do a total cost analysis, total cost is basically time to science. Time to science is really core hours cost plus design time cost. So in a supercomputer, it's about, let's say, 300K plus 4 to 5 days. But on a cluster, it's a little bit less in terms of money, but really it's 6 months to 3 years. So it's really not feasible, right, to do this. So that's why people take shortcuts. That's why people reduce their design space. They don't want to run 12,000 cases. They probably want to run 1,000 cases, let's say. So I'm coming to the end of my talk here. What we have developed at Argonne is this forum to work with the industry. It's called Verify. Stands for Virtual Engine Research Institute and Fuels Initiative. A lot of words, but it basically is a consulting service for industry to work with us. So the industry would come to us with a problem of their interest, and we try to provide HPC solutions. And we also have workshops with certain themes. So the next workshop will be in November with the theme of predicting cyclic variability using simulations. And this is really the mechanism with which we work, being in a national lab. So we have access to DOE Office of Science people. We work with the computational scientists at Argonne who actually help us scale the code. We work with the chemists at Argonne who actually help us write chemistry for these fuel molecules of interest. We are mostly funded by EERE. So we actually interface with DOE Office of Science people and try to develop engineering level models. And then we have this Verify consortium that basically enables these engineering models to be used by OEMs, software vendors, and oil and energy companies. I'm not going to go into details, but these are all the companies that we have worked with in the last couple of years, and we also work with the academia quite heavily. We have developed several models. A lot of these are actually then scaled on an HPC system. So these models are first developed, validated, and then we also spend a lot of effort in trying to make them scale on a supercomputer. This is my last slide. I'd like to say that HPC is actually an enabler for simulation-based engine design. And it allows us to use high spatial and temporal resolutions, robust turbulence models, detailed chemistry, and we can solve one-of-a-kind problem. And the benefits are really unprecedented insights into the combustion processes and increased predictive capability. And in many cases, working with industry, we have been able to modify their best practices. So whatever we have developed, the industry folks have been actually able to take it into their in-house workflow, which has been a great success story for us. And we were quite happy. We won a couple of awards. In 2014, we won the HPC Innovation Award by IDC. This was in collaboration with Caterpillar and Convergent Science. In 2015, we won the Federal Lab Consortium Award for Excellence in Technology Transfer to Convergent Science. So it has been 2 years. We haven't won any awards, so we are working on it. So that's pretty much it. This is my team, and I'll really like to acknowledge the funding sponsors for funding this work. Thank you very much.
Can you describe a little more the award that you got for the federal technology transfer? What was the technology transfer that you did, and kind of how did that work?
Yeah, so we actually developed some technology for spray modeling, two-phase flow modeling, and we actually scaled that technology, demonstrated that that model will actually scale on a supercomputer. So that's the technology that was developed and transferred to Convergent Science.
So did Convergent Science pay for that through the Verify program? I mean, they paid you to do that for them?
So we have been working with Convergent Science for many years. So the model that we have is that an industry would come to us with a need and the software of their interest. Many times it has been Convergent Science. So the industry is actually driving what software we use and what models we develop and implement.
Maybe I should be clear, model, I don't mean computational model. The business model is that the company would come and pay you to do the development work, and then you transfer the technology back to them?
So we have done both ways. So we have also had DOE programs where we have CRADA projects where whatever we have done is actually published and gone into open literature.
Sure.
But then within Verify, we have also done work where the industry has paid us to develop models and implement it into the code of their interest.
Like through a work for others or something like that?
SPP, for example.
SPP,
yeah,
okay.
Yeah.
Thank you.
You're welcome.
I'm sorry, I have to ask. You had the dream situation where you have complete modeling capabilities and such. Do you have any sense what the limits are of an engine to deliver, say, horsepower or miles per gallon, if you have that dream, scenario computationally?
So thermodynamics actually limits the amount of efficiency that we can get out of fuel and an engine, right? So the thermodynamic efficiency is not going to go beyond 60%. For a heavy-duty engine, we are already at 54, 55%. So if we can actually do this co-optimization, the hope is that we will be able to go that 0.5% more, maybe that 0.75% more. And that's going to win awards. In the ERE space, if you can improve fuel efficiency by 0.5%, it has a huge impact on the nation. So typically, people win awards by improving efficiency by 0.5%.
Cool.
Any other questions? Yes?
So you were describing this multivariate study of these sensitivities to both model-based parameters and then operating parameters or geometric parameters. Can you elaborate on anything that was unexpected that you learned in that study?
That's a good question, actually. So the first study that we did was actually on a diesel engine, where we had a lot of experimental data, we had a lot of understanding of the data. So we really wanted to validate this GSA tool. And in that study, no surprises came out, actually. So we were quite happy that the GSA tool was giving the right trends that we were observing in a standard diesel engine operation. So then we moved the tool to this gasoline compression ignition, where we are trying to compression ignite a gasoline fuel. And we saw a lot of surprises. For example, if you were looking at NOx, we observed, these are all simulations, right? We observed that model parameters were dominant in sensitivities to NOx. I would have thought that fuel properties would have had more influence on NOx, for example, for this GCI combustion. I would have also thought that the start of injection timing would have had a big influence on NOx. So we found some interesting things. So we ran a lot of cases, right? So we had a lot of data. So then we started going back into the data, doing some more data analytics, and figuring out why we are getting these results. So eventually we were able to explain why model parameters were more sensitive to NOx. But initially it was a surprise.
Can I just ask a follow-up about the point? What was the time duration of that work? And what were the process learnings that you think were really important to get you to the outcome?
Right, so maybe I didn't explain the workflow very well. So the first step for us was to actually implement this Swift algorithm that's developed by the math and computing science folks at Argonne. So that actually allows us to run these thousands of cases in a seamless fashion. Otherwise, it's almost impossible to run these cases. So once we were able to launch these cases, the next step for us, once we were able to integrate this Swift capability, we actually talked to our experimentalists, Steve Ciatti in this case, to figure out what are the uncertainties in his experiments. Then being modelers, we tried to figure out what are the uncertainties in our models. And again, uncertainty in our models for a new combustion system are much higher than if you were just doing diesel combustion simulation, where we know the models very well, right? So that was the second step, to really identify the uncertainties from an experimental standpoint and from a modeling standpoint. Then there was a lot of coding to really make this process seamless, where we created 12,000 folders. Each folder had like 30 files. That's how complicated each engine simulation is. And we generated terabytes of data. And then we figured out how to actually process those terabytes of data. Some of them was just simple Python scripting. For example, if you're looking at CA10, NOx, soot, the data files were already written out in a way that it was easy to extract this information. But to really look at the 3D visualization, it was some effort. And We actually did the 3D visualization on Cooley that's actually connected to Mira. So we did not bring the data back to our cluster or our desktop to do the visualization. The visualization was done in a file system that was connected to Mira. So that was a 1-year project, actually. It was possible due to the 60 million core hours that we had.
Okay, thank you very much.
Thank you.